Namaste, this is Dr. Asha, working as Associate Professor in the Department of Civil Engineering, Maharaja Institute of Technology, Mysore. I am here today to discuss on the topic centroid. So basically, we shall understand the definition of centroid first. What is centroid? So it is a point on a lamina. So we shall understand the centroid with its basic definition. What is a centroid? So let us assume that we have a rectangular plate over here. So where is the centroid then? I will just write here is the centroid. Why I have located the point here itself? Because it is the point of intersection of two diagonals. It is represented by letter G, which has two coordinates x bar and y bar. So where am I supposed to consider as x bar, or from where am I supposed to consider the distance as or the ordinate as y bar? Here I shall write the reference center O. So now the representation of the axis, or what we call as reference axis. So here we have two reference axes. One is x axis and the other is y axis. So now comes x bar and y bar. The distance that are to be considered from x axis up till this point is y bar, and the distance from this point reference will be the y axis, that is for coordinate y bar. So for x we consider y axis as the reference, and for locating y bar we consider x axis as the reference. So now I will define centroid as a geometric center. Geometric center, wherein the area is concentrated, or the total area is concentrated. Very specifically, we locate centroid for two-dimensional plane figures. So we shall understand first why are we considering it for two-dimensional figures itself. So let us take an example of this. Here is a solid body. Fine. So at a glance I just feel it as a rectangle. But no, it is not a rectangle. It is a solid body by default, or I can tell this as a cuboid, because it is three-dimensional. Means to tell it has width, height or length, very importantly the thickness. So this is a three-dimensional figure. So if I am supposed to consider this as a two-dimensional figure, or if I am supposed to tell this as a rectangle, then I shall consider only a single page of it, wherein the thickness is negligible. Means to tell it has area but no mass. Then this is a two-dimensional figure. I will tell this as a rectangle now, because it has the dimensions only width and length. As mentioned, thickness would be negligible. So now we shall consider certain examples for two-dimensional figures. Rectangle, circle, triangle, etc. So now moving on to the examples for three-dimensional figures, specifically cuboids. Fine. So now I just tell everything relevant with two-dimensional figures. We will be locating the centroid, while for three-dimensional figures we locate or we are concerned with center of gravity. So what is this center of gravity? It is the point wherein the total weight of the body is concentrated. So here we are concerned about the total weight of the whole body. Means to tell that particular point itself will be a balancing point. So then the center of gravity is a balancing point wherein the overall weight of the body will be acting. So now, as of this module is concerned, we will be confining ourselves to the two-dimensional figures, that is to locate the centroid. We shall understand the centroid very specifically by this example. So, as we know, this is the reference center. Let this be the reference axis. Reference axis are the x-axis and y-axis. So, now the next important one has to know prior to the startup of centroid is the centroidal axis. So, the centroidal axis is the axis wherein we are locating the centroid with its coordinate or the points x bar and y bar. So now it's very clear that by definition centroid is the geometric center of a lamina or the geometric center of a plane figure. How are we locating the centroid then? Do we have to remember the coordinates every often? Means to tell for each and every geometric figure, do we have to remember the ordinates? Not necessarily, and that is not even wise to remember the ordinates. Rather, we will have to be very precise of positioning this reference axis. Now, if we are looking at this diagram, I can tell here the lamina is in the first quadrant or the centroid is in the first quadrant, right? We prefer positioning the reference axis in the first quadrant because the signs will be positive for both the points, that is for x bar and y bar, if we select first quadrant. That is the main intention. So now the next thing is that we are not supposed to remember the coordinates. In spite, it's fine if we remember the positioning of the axis. So now if I tell the dimension of this rectangle as b by d, so then what is x bar and y bar? As discussed previously, x bar is the point considered from y-axis as the reference up till this point. So this is x bar. while y bar we consider x-axis as the reference. So that is x bar and y bar. So what is x bar and y bar here? It is b by 2 and d by 2. So the dimensions of x bar and y bar is b by 2 and d by 2. Both will be positive itself. So if I consider or if I locate the reference axis on the other side, obviously that will be in the fourth quadrant. The dimensions or the points will be negative. So for ease and convenience, always we position the reference axis in the first quadrant itself. So what about the position or the orientation? Does the centroid or the point change if we change the orientation? If we consider the example of a triangle wherein the G is located here, G is the centroid, fine, and here is an axis, fine. So now I have the apex here and the base at this point, right? What if the orientation is changed? Let us see that whether the orientation is changed. So does this point change? Definitely not. The point of centroid remains in the same point. Only thing is that we have to see or we have to be careful, or very importantly, there is no change in the point of centroid if the orientation is changed. Next, moving on to the location of centroid for some of the basic geometric figures. Location of centroid from first principles. We shall understand that with a basic expression, that is, let us consider a solid body which is divided into n number of elementary figures or areas. Here is our x-axis, this is y-axis and the z-axis. So now, as mentioned, we will be locating the centroid at a point where the total weight is concentrated. So now I am telling the total weight of the body is concentrated here. This itself is the point that is to be considered. Next, here is the thickness. Let this be Wn, whose reference points or ordinate points are xn and yn, while here it is x bar and y bar. Let this be W1, with x1 and y1. So now this is the point which has x bar and y bar. Further, the whole body is divided into n number of smaller elements whose areas are defined here. Fine. So the thickness of individual elementary figures is represented by T. Fine. So now, as we all know, applying the principle of moments for y-axis, then Ax bar is equal to A1 into x1 plus A2 into x2. So now x bar is equal to x bar is equal to summation of Ax by summation of A. Similarly, if we are applying the principle of moments to y-axis, if we are applying principle of moments to x-axis, then Ay bar is equal to A1 y1, A2 y2 or y bar is equal to summation of Ay by summation of A. This is what we are supposed to remember. So now, the next thing is that we'll have to understand the axis of symmetry. We'll understand the term axis of symmetry. So let us assume that here is a geometric figure. The term axis of symmetry is very easy to understand by a term known as the mirror image. So that axis which divides the total area into two equal parts, or the axis of symmetry is the one which gives the mirror image of one another. What if I have the diagram as such? So can I tell this as the axis of symmetry now? No, because I do not get the mirror image of one another here, wherein I have a rectangle here, while I have a combination of a rectangle and a triangle here. So I do not get a mirror image here. Fine. Likewise, if I consider a circle, do I get the axis of symmetry? Yes, I do. But where do I locate the centroid now? It is at the point of intersection. So we'll have to understand that the centroid always lies on the axis of symmetry. The centroid always lies on the axis of symmetry. So what if I have the combination of geometric figures? We call that as composite figures, wherein I calculate the area by dividing the given total figure by dividing the whole area into defined geometric figures. By then I find out the area individually and sum up the areas. Similarly, I find out the centroid for each and every defined geometric figures, and then ultimately find out the point x bar and y bar by merging of all the individual geometric figures. So now we shall derive an expression to locate the position of centroid in a rectangle from first principles. So let us consider the square A, B, C and D. We are deriving this expression based on the method of integration. Means to tell, we know that this rectangle can be divided into n number of individual strips. Here we are considering the horizontal strip. The dimension is B by D, while the thickness of this is dy. So now let us consider the area of the rectangular strip or the elemental strip as B into dy, because I know the dimension here is B into dy. Therefore, moment of the elemental strip is equal to B into dy into y. Next is sum of the moment of the elemental strips, because I have taken the moment of an individual elemental strip, but I have n number of elemental strips throughout. So summing up of all those things is integral of B into dy into y from 0 to d. Therefore, it is 0 to d. B will be the constant. Next is y dy. So upon integration, it is B into y square by 2 from the limits of 0 to d, that is equal to B into d square by 2. So let this be equation 1. So now this is the sum of the moment of the each and every individual strips. So altogether I have this expression. So now my concern is to find out the centroid for the overall area or the whole area. So now moment of the whole area from the base AB is equal to B into dy into y bar. So now from the base AB is equal to base into height into the centroidal distance. So we shall name this as equation 2. Now applying principle of moments, this is the first expression, BD square by 2. Here is the second expression, BD into y bar. So I will have y bar is equal to d by 2 upon simplification. So now where is the centroid located for this rectangular plate? At a distance of d by 2 from the base. Here is the centroid. But if I consider a vertical strip, I will get x bar is equal to b by 2. If I consider the vertical strip and derive the expression, I will get x bar is equal to b by 2. So now where is the centroid located for this particular rectangular lamina? At a distance of b by 2 and d by 2. Moving on to the next derivation, or we'll consider the next geometrical figure. We shall derive an expression to locate the position of centroid on a symmetric triangle. So now we shall consider a symmetric triangle A, B and C, whose base is represented by B and height is represented by the term H, while I consider a small elemental strip of thickness dy. So now the smaller triangle which I can see here will be named as A, B dash and C dash. So what is the width of this smaller triangle? It is B dash. So now we know from similarity of triangles, from the principle of similarity of triangles, we will compare the triangle ABC and triangle A, B dash and C dash. So what is the height of the smaller triangle? So here this is the point Y, that is the distance from the base of the elemental strip to the base of the bigger triangle, that is Y. So now I have this height as H minus Y. So now we shall compare the height of the smaller triangle and the bigger triangle. So height of the smaller triangle is H minus Y and height of the bigger triangle is H, while the base width of the smaller one is B dash and the base width of the bigger triangle is B. So now by cross multiplication, B dash is equal to B by H into H minus Y. we shall note this expression as 1. So now in order to get the moment of the whole lamina, we are dividing this whole lamina into individual elemental strips. So first of all, we are finding the moment of the small strip we have considered. So now moment of the elemental strip that we have considered. So we can just see this strip is a rectangle. So now here it is b dash into dy, b dash into dy into the perpendicular distance is y. So now substituting the value of b dash here, b by h into h minus y into dy to dy. So now b by h into h y minus y square dy. So upon opening the brackets, we get this expression. This is the moment of the elemental strip, means the single strip. So but all we want is for the overall area. So wherein we have divided into many number of strips. So next is sum of the moments of the elemental strips is equal to integral of b by h into hy minus y square dy. So from 0 to h. So now upon integration, or first upon removing the brackets, we get hy dy minus integral of y square dy. So now here b by h is a constant. Again h is a constant there. So upon integration of y, we get y square by 2 from 0 to h, the limit is 0 to h, minus y cube by 3 from 0 to h. So now b by h into h square by 2 minus h cube by 3. So now b by h into h cube by 2 minus h cube by 3. We get b by h into 3h cube minus 2h cube. Now upon simplification, we get b by h into h cube by 6. Therefore, we get bh square by 6. So this is the expression. We shall name this as equation 2. Further, all we have there is the expression for the individual or the overall strips whatever that we have divided. But now considering the moment of the whole area from base BC, area into y bar. So what is the area of the triangle? Half into B into H into y bar. Let this be equation 3. Now applying the principle of moments, we shall equate equation 2 and equation 3. BH square by 6 is equal to half into B into H into y bar. While finally we get y bar is equal to 2, B and B is cancelled here, again H is cancelled. So we get y bar is equal to H by 3. So now where is the centroid located for a symmetric triangle from base? It is located at a distance of H by 3 from the base. This is the expression for the symmetric triangle.